Give floor to our next presenter. And please welcome Büntgen Ulf from the University of Cambridge. And Büntgen Ulf is a member of the Russian Academy of Sciences. I thought I should mention that he is an international member of the Russian Academy of Sciences. And his presentation is titled New Frontiers in Tree Ring Research, Rethinking Dendrochronology. Over to you.
Hello, everybody. Can you hear me?
Да, мы вас слышим хорошо.
Yes. Yes, we can hear you very well.
Perfect. So thank you very much, first of all, for the invitation. It was a pleasure to attend this conference so far. Great presentations, very stimulating and wonderful opportunities, and many of them to collaborate and strengthen our collaboration. So thanks for all the speakers and the lively discussion so far. Gareth asked me to talk a little bit about tree ring research. That's what we are doing in Cambridge, and I thought I show a couple of examples rather than going into detail, to give an overview of what we are currently doing with wood, with living trees, and also material from subfossil wood. I will obviously focus on research projects ongoing and more recent projects in Russia. I'm doing that together with many colleagues in Russia, mainly in Krasnoyarsk, but there are huge, it's a huge consortium of people that have been involved in several publications that you can see here. So the research I'm going to discuss today relates to these publications, and the topics or subtopics I will touch. I'm going to start very, very simple. What is a tree? I have the idea that all of you have some kind of imagination in mind if I would ask what is a tree. Let's see if that maintains. Then we're going to talk about the so-called Lalia, late antique Little Ice Age. I will use examples from Norilsk to explain the divergence problem in tree ring research. And the last slides for this afternoon are coming from Chukotka, from northeastern Siberia, where we hope to conduct more research at a wonderful lava flow field of the Untitled volcano. Okay. What is a tree? That's a simple question. You would also give me most likely a rather simple answer, but let's see if that holds after a couple of minutes. This is a picture I took several years ago in northeastern Greenland, coastal East Greenland, and you are looking out to the North Atlantic. Not a lot of vegetation. If you turn around, it's not looking different. So difficult to find the forest, difficult to find trees. But if you are very cautious, there might be a little bit of vegetation down here between the rocks. So this is Rhododendron laponicum. I would now argue this is a tree. You see the scale on the right side, a hand. This is the hand of Fritz Schweingruber, the late Fritz Schweingruber. So we have an idea about the size of this plant. We have a canopy, we have a stem, we have a root system. So from a morphological perspective, you cannot distinguish between a large tree and a small plant like this one here. Now you may argue, okay, trees, tree ring research, dendrochronology, that depends on very old growing individuals to be able to reconstruct back in time. If we cut this stem here, so we take a thin section through the stem, we can count 240 rings. So this is a wood and anatomical thin section of Rhododendron laponicum from northeastern Greenland, and the plant, the tree, it's a dwarf shrub, is more than 200 years old. So the whole point I want to make here as an introduction, if you think about tree ring research, you may expand your perspective, you may expand your target areas from the traditionally forested areas into the tundra. This is very relevant for environmental research in Siberia, in Russia, because there are vast areas that are not covered by taiga, not covered by what we would consider forest if we think a tree needs a certain height, but it's beyond forests. And if we are interested in reconstructing tree line dynamics, vegetation dynamics, also the turnover time and capacity to sequester carbon, smaller plants like these dwarf shrubs are becoming very, very important if we are introducing a field that is called wood anatomy or quantitative wood anatomy into more traditional dendrochronology or dendroecology or dendroclimatology. We are immediately open a huge geographical area which we have formerly neglected. So this was just a small introduction. If you think about tree ring research, also consider understory and vegetation beyond the upper and northern tree line. Okay, now the first example, the late antique Little Ice Age. This image shows another anatomical thin section. We see a couple of rings, and in the middle we see a structure, an anatomical anomaly, a so-called frost ring. Dendrochronology, we can date this ring in the middle. This is the year 536, so almost 1,500 years back in time. It is the result of a very distinct cold spell. With the anatomical image here, we are able to date not only the year, but also the season. So this frost spell most likely occurred between June and July. It has been recorded here in a Larix sibirica from the upper tree line in the Altai. So let's go back a little bit. What we did, roughly 10 years ago, we published the first paper in Science where we were able to reconstruct both precipitation and temperature. Precipitation in the upper part of the image, temperature, summer temperature in the lower part for Central Europe. So this has been built on data from Europe and the European Alps. And the most striking feature is the anomaly, both in the hydroclimatic cycle, but also in the summer temperatures around the 6th century. At that time, we had no idea how to call it, so we thought we may associate it or it coincides with the Great Migration period. Then we expanded our perspective from just one study in Europe. We went more into inner Eurasia because we wanted to see, are we able to reproduce the climate history from Central Europe towards inner Eurasia. This here is a picture from the Altai Sayan Mountains. We are looking southwards, so south of the mountain range would be the Mongolian border. It was a great trip, fantastic people in the Tuva province. And we are interested in collecting samples, both from living trees, but also from dry dead material. The tree line here is around 2,300 meters in elevation. It's Larix, it's a very undisturbed tree line ecotone that allows us to find dry dead wood remains that are lying around for several hundreds to thousands of years. Now, just briefly, the upper part of this figure, these horizontal light green horizontal bars represent the core samples of both living and relic material. We have a total replication of almost 800 trees that enter the chronology, and we are spanning the last 2,000 years, so the Common Era. Then in the middle part, in the C part, you basically see the germination ages, periods when more or less trees started to grow. The blue line, the D part of the figure, refers to changes in tree line position, so at which height were these relict in situ or living trees cored, so that's more or less stable over the last 2,000 years. And the lower part is not a climate reconstruction, but it is a tree ring chronology. You see more uncertainty in the earliest part, so let's say before 500 Common Era, and in the last century. Everything in between is very stable. This is a normal phenomenon. Tree ring chronologies, like most other time series, are most prone to error, methodological or data-related error, both in their earlier and late years. Now, what we are doing, we are comparing the new data from the Altai, the red curve, with the existing data from the European Alps. And the striking feature here is that both totally independent tree ring width chronologies over the last 2000 years are showing a very significant high degree of coherency, both in the year-to-year variability. We also see that decadal fluctuations are perfectly captured, and long-term trends. So two totally independent, absolutely independent time series over the last 2000 years, and they reveal a lot of coherency. The most striking feature, again, is captured now or is reproduced in the Altai, what we earlier saw in the Alps, this very strong temperature depression in the 6th century. If we zoom in, this is what we see. Again, it is the year 536. Earlier, you saw the frost ring. Now what you are seeing is a blue ring. So this is a thin section, double stained with astra blue and safranine. Normally, wood turns out to be red because it's lignified. The cell walls are lignified. And everything that is blue here, this is not lignified. So what we are finding here is evidence for a temperature or thermally induced lack of lignification exactly in the year of interest, 536. Now we are transforming the two chronologies into temperature reconstructions for the last 2000 years. Most striking feature both in Europe and in inner Eurasia is the occurrence of the so-called late Untitled Ice Age, a very sharp onset of this period, exactly the year 536. And now it's under debate or questionable how long did this cold spell last, several decades, up to a century. The lower part of the figure, you see the forcing. So we not only know that there was a very cold period, likely or most likely the most severe and distinct summer cooling of the last 2000 years, the so-called late Untitled Ice Age. We also know the causes, the drivers, a cluster of large volcanic eruptions, with the first one starting in 536, and there was another large eruption in 540 and 47. So this cluster caused feedback mechanisms, loops. So sea ice extent and changes in the albedo. We heard that earlier today, how this can have long-lasting and large-scale climatic effects. We heard it in the opposite direction. If we have a decline in sea ice extent, this affects the albedo also. Here we have it in the other direction. And then towards the end of the so-called late Untitled Ice Age, you see that with the dashed gray lines, so the dark black spikes, so these black lines down here are referring to sulfur depositions and ice cores, Antarctica and Greenland, as a result of large volcanic eruptions. And the gray dashed line refers to solar activity. So again, an indication for a negative forcing that coincides with this period of interest. Then we reached out to the historians, and the historians were very interested and came up with a huge calendar of what happened during this time across Eurasia. It is not only the onset and establishment of the first plague pandemic. We are aware of the Justinianic plague that started in 541, exactly when this cooling kicked in, but also a lot of migration, larger scale migration from inner Eurasia, both affecting the Old World in that time the Old World or Europe, and at the same time also the Chinese dynasties. So lots of societal unrest, and you can also call it turmoil, that coincides with this cooling episode. At that time, a couple of years ago, we had a couple of workshops organized in Krasnoyarsk with the aim of combining different lines of evidence. So not only to understand the climatic anomaly better in the 6th century by comparing and integrating tree ring-based climate reconstructions with glacier dynamics, but also with climate models, and to work closer together, build up more quantitative relationships in the assessment of data from the archaeologists. This is still an ongoing task, and we are constantly in exchange with people that do provide information, independent lines of evidence, both for climate variability, but also human history for the 6th century in Inner Eurasia. And then most recently, so this year, again, in the first slide I showed you was evidence for the late Antiquity Ice Age in Europe. Then we extended it from Europe also to Inner Eurasia, to the Altai. And now we just published a paper on the northern hemispheric extent of this period. So what you see in the A map, these are 9 sites that we currently have. All these 9 sites are providing tree ring width data that cover the last 2,000 years. And the map is interesting for this workshop because the vast majority of sites are coming from Russia. We have 3 sites in northern Siberia, Yamal, Taimyr, northern Yakutia, and the Altai. We have only 3 sites in North America. There are 2 sites, 1 and 2, in the western US. 1 site in Quebec, Labrador, which is number 3 here. In Europe, we have the European Alps. You are aware of this site from the first part of the presentation. And we have a very strong record of tree ring data, very comparable to what we find on the Yamal and Taimyr Peninsula from northern Scandinavia. The B part, so the middle map here, shows us the summer temperature signal of these 9 sites in space. And most interestingly, over the 2 sites in the western US, we don't see any red color. So we are actually losing 2 of the 9 sites, site 1 and 2, the Great Basin and southern Colorado. They just don't capture a clear summer temperature signal. So out of 9 potential sites that cover 2,000 years that are currently globally available, we only have 7 remains, and we see the area is basically covered. The C part would be if we correlate temperature measurement. Someone is coming home from school. Huh? Okay, the C part, but it's not at my house. The C part shows if we correlate temperature measured against temperature measured, so basically real world, and we see in B the proxies are more or less resembling the real world climatology. Okay, this is an example just to show you where do we get wood from that covers the last 2,000 years. This is a beautiful picture taken, it's a Lena Delta. This is an example. You can also go to the Yana, you can go to the Indigirka, the Kolyma, all these great river, the catchments, the big river systems are trapping lots and lots of wood. It is a fantastic archive for us to expand these long chronologies, and that's also why most of the 2,000 plus year-long temperature-sensitive chronologies are currently coming from different parts in Russia. So that's the new Northern Hemisphere or Eurasian plus summer temperature history. Again, the last 2000 years are covered, and we see evidence for the late Untitled Ice Age in the 6th century. If we are comparing our new reconstruction, these are the upper two graphs, we see, yes, we have a recent warming, so it's more orange in the last century, but we also see periods during medieval times and again in the late Roman period that were also red, so they were warm. If we compare that to a multi-proxy large-scale temperature reconstruction that was published last year in Nature by the Pages Consortium, which describes more a hockey stick kind of temperature history, so colder conditions and the very distinct most recent warming. Our new reconstructions for Eurasia and the North Atlantic sector just demonstrate much more natural summer temperature variability, and we see the most distinct cooling episode coincides here with the late Untitled Ice Age, starting again in 536 and lasting for at least a couple of decades. Again, we are zooming in. Now we have another blue ring. You see 536 and 537, red again, but still a very small ring. So this is a resolution we are getting now from tree rings. We're getting that, you know where the trees are coming from a relatively sparse network of 2,000-year-long summer temperature-based or tree ring-based summer temperature reconstructions. And an interesting thing is that all these reconstructions are capturing the signal of large volcanic eruptions, whereas multi-proxy approaches that also include data from lower resolution archives, lake sediments, ice cores, that probably contain some dating uncertainty. Their response after large volcanic eruptions is almost zero. So you see the gray line, that is a Pages reconstruction compared to the tree ring based reconstructions, the orange and dark red one. They show a cooling, very distinct coming in relative to the year of the eruption. So the first year after the eruption is a cooling, and that lasts for at least a decade. And it's a robust pattern if we compare it over the first 12 eruptions from the year 100 to 1200 Common Era. So basically before into medieval times, and then from medieval times until the onset of the industrial period or the Anthropocene, another 17 eruptions, again, decade-long cooling reflected in the tree rings, and only a very moderate cooling in the multi-proxy compilation. The final figure of this publication is the new temperature reconstruction, large-scale Eurasia or Eurasia Plus, which is in the Eurasian data plus the Quebec data. Important for this workshop, most of the evidence comes from Russia. That includes Taimyr, Yamal, and northern Yakutia, plus the Altai. The coldest period on record, the coldest year of the last 2,000 years is the year 536. Then we have some variability, but generally this period is distinct, cooler than the long-term average. We have two relatively warm periods, one at the end of the Roman period in the 3rd and 4th century, or the 3rd century mainly. And we have two distinct warm periods just before the year 1000 in the 990s and around 1020, 1030. Okay, time is running. Another example, I want to explain you the so-called divergence problem. We therefore go to Norilsk. So here we are a little bit east of Norilsk. You see why that makes sense. So lots of forest decline, devastation, environmental devastation, large scale. So you see Norilsk here. The main dominant wind direction comes from the west, northwest. So the largest amount of pollution, the largest spatial extent and intensity is east and southeast of Norilsk. We see that here in gray on the background map, the percentage of vegetation disturbance due to pollution. We see the industrial sectors with the yellow stars, and in green, our reference site. So tree ring site of the boreal forest of the taiga, west of Norilsk, outside the polluted area. And then we have a gradient from site 2 all the way to site 8, predominantly larynx, but there are a couple of sites here towards the southeast where we also sampled spruce. The color refers to mortality degrees, red totally dead, green still alive. Now let's look into the data. We were sampling living and dead trees. Whenever trees were living, we sampled them. Otherwise, we sampled the dead material with bark on, so the outermost ring can be dated. And we see right from around the 1950s on, from the 1960s even stronger, we see the decline in forest vitality, and the percentage of living trees is going down. You could also show it inversely and say the amount of dead trees is increasing. We have up to 100% dead trees at these sites, and the further we go east, southeast, you remember the reference sites, the tree mortality is small and the trees are still growing. We also measured sulfur, copper, and nickel content in these trees, and we could see just the year before these trees were dying, they exhibit the highest level of pollution, sulfur, copper, and nickel. Wait, but let's see, let's go one back if possible, yes. But then there are also the surviving trees. They contain a low level of pollution, but we were interested in these survivors and thought, okay, the trees may still live, but they are suffering. And we are now, and that's why I'm calling it to explain the divergence problem. We know since around the 1970s that tree growth, conifer tree growth of the boreal forest is not tracking summer temperatures as good as we would expect it. So temperatures are going up, whereas tree growth is slightly declining. And here we are, for the very first time modeling, we are using a forward model to simulate tree ring widths. We have the measurements in green of the surviving trees. We see high growth rates here in the first half of the 20th century, and then we have a constant decline. And now we are modeling tree growth, and we would actually see an increase, which we don't see. But on the B part, we are implementing into the forward model an additional forcing, a so-called dimming factor, which we assume is a result of large-scale pollution, sulfur emissions. So we have something that is called Arctic dimming. And if we are implementing this factor in the modeled tree growth perfectly tracks the measured one. So we are exactly able to explain this so-called divergence, the inability of formerly temperature-sensitive tree rings to track recent warming. We are now able to explain it by increased Arctic pollution, mainly sulfur depositions into the atmosphere that is shielding incoming radiation. Okay, now towards the end, I'm showing you a couple of slides from northeastern Siberia, from Chukotka. This is the Anui volcano complex. It was discovered in the 1950s by Bilibino, a geologist from Moscow. You see the volcano in the back, you see the lava field in the front, and you see dry dead material. That's where we are. We are east, far east of the Kolyma still in its Kolyma catchment. We are around 250 kilometers west, slightly southwest of the Büntgen Lake. And you see in the inset, that is a cone of the volcano. It looks very recent. To my understanding, to everything what I know, the dating hasn't been confirmed at all. It is very dubious. So we are interested in dating the eruption. The last one, the star here refers to the cone. And then we have a lava field of 50 kilometers. So a massive lava flow. And that is perfect. We have lots of lakes, just recent or dammed lakes by the lava flow. And you see down in the images, it is this perfect situation for dendrochronologists to find old material, dry dead wood that is basically on the lava flow. It is disconnected to the water table or soil, so it can last very, very long. And lots of rivers, riverbeds, lakes, where there is a potential to find relic material buried in the ground or under the water level. So this is where we have been last year. I said the lava field is 52 kilometers long. It is massive. It bears a huge opportunity to find relic material for an area where we generally don't have material. So it's a perfect site. And that's where we want to continue our work in the next couple of years. This year we had to cancel an expedition. Okay, thank you very much. That was a lot. I hope I was able to show you tree ring research goes far beyond just counting a couple of rings. We are able to provide temporal information at annual resolution and always absolutely dated to a vast field of environmental and natural science fields, also to the humanities, if we are trying to link climate variability and human history. And the potential to do tree ring research in Russia remains incredibly. So I'm always very, very pleased to have the opportunity to collaborate with many of these fantastic colleagues I have in Russia. So thank you very much for listening.
Большое спасибо за очень интересный доклад.
Thank you very much. That was an amazing presentation. Unfortunately, my battery is low, and I mean on the computer, and I don't see if there are any questions in the chat. Can someone please help me out and make sure that there are no questions in the chat?
I can't see them either.
Нет, по-моему, да, в чате вопросов не появилось.
Yeah, it looks like there are no new questions in the chat. Anyway.
Okay, better.
I have a question. I will use my this opportunity of being a moderator. This case from Norilsk, where you are simulating the impact of pollution on the annual growth of trees and tree rings. So what are the main parameters that you use for simulation under normal conditions? If there is no pollution, what are you using? It's temperature. What else is there? What are the normal model parameters?
So modeling tree growth at the northern or upper tree line is relatively easy because the main limiting factor of tree growth under such conditions is temperature. So the model would get, or the tree would get enough precipitation from rainfall and snow melt. So this is implemented in the model. And then temperature variations that are also implemented, summer temperature variations in the model, they are usually the closest related to the ring width parameters, density or ring width we are seeing, because it's a predominant limiting factor. And that's also the reason if we are simulating or modeling tree growth in such environments, it usually tracks summer temperature very closely. That's why we can use these trees almost like a thermometer. In this case, it doesn't or it works. So, but the reality shows us that the trees are not tracking the warming anymore. And we were wondering, or we had no explanation for this so-called divergence for several decades. And just the Norilsk example made us think what's actually going on in the surviving trees. They obviously suffer, so they are not dying, but they don't grow that good anymore. And then we started to play and implemented a new parameter, which is then pollution. So what we are not including, and one could, but this is not the main aim of dendroclimatology, like stand parameters. We know we cannot model the growth of an individual tree. That's too complicated. But if we are operating more on the regional or larger scale to emphasize the common signal, then it works. So the model gets simpler and easier if we are expanding the scale a little bit. So I'm just saying that you don't think that we are able to model tree growth. It's very, very difficult, and each tree behaves different. But then there is this common signal that is often temperature or climatically induced.
Спасибо большое. Очень интересный доклад.
Thank you very much. This is fascinating.